That's fine.
I promise we will not do so much algebra in the subsequent lectures, and will be possible to understand them even without having to look at so many equations. But we will continuously have some equations or the other. Right? The theory was basically developed in this pioneering paper by Abe, Bartholdi and Ernst, which I gave a reference to in the list, and is done quite well in the book by Ernst, which is reference 1. And there is a good article by Turner, which is also given in our list of references. The first two of these use what's called a super operator notation. I mean, I don't really have to call it super operator algebra, but more of a super operator notation. We will not do that, and we will basically, the main motivation for using super operator notation is to describe relaxation properly. We will introduce relaxation phenomenologically, and so we can use simpler approach, and that's what we are going to do. We are going to divide this lecture into several subsections, and in the first one I'll briefly tell them what is the spin Hamiltonian that we are going to use. I will introduce a little bit density matrix, and then they calculate the time evolution of the signal in 2D experiment, two-dimensional Fourier transform, line shapes in 2D, and filtering in 2D. So basically, this is what we are going to do today. The spin Hamiltonian in NMR and high resolution NMR of liquids is basically consists of two terms, the Zeeman term and the spin-spin coupling term. And the spin-spin coupling term, the Zeeman term is written down as a chemical shift term and plus a J term, which is a spin-spin coupling term. And the J term is a scalar product and written as I1 dot I dot I, which I can write out in expanded form as Ixj plus Iyj plus Izj. We make often an approximation in high resolution NMR spin Hamiltonian that we only retain the Z component of this term, because if the chemical shift between the two spins is large compared to the J coupling, then the mixing created by the X and Y term can be neglected, and that is called the weak coupling approximation. And that weak coupling basically is when Jij is much less than omega I minus omega J. And as I showed you, a difference in the spectrum of a weakly coupled spin system is something like this, while a not weakly coupled spin system where the X and the Y terms are important is something like this. And so often we will use the weak coupling Hamiltonian. So basically we have the chemical shift and J coupling. Under the presence of a radio frequency, you have an additional term in the Hamiltonian, and I represent it as a radio frequency term, and we write it down. It is an oscillating term with the frequency omega and amplitude gamma h1 applied along x-axis of the laboratory frame. Okay, x-axis of the laboratory frame. That means maybe I should draw you a frame. And the magnetic field H0 is along this direction. That's the basic magnetic field. And we apply the radio frequency along this direction. And then the term that we have written down will be of this type. Usually it's an oscillating term, and we divide it into two counter-rotating parts. And one of the rotating parts is near the Larmor frequency, and that is the useful one. And the other part, which is which is counter-rotating, we throw away in the NMR experiment. one can very easily see what I have written down there is two counter-rotating parts, one which is like this, Ix plus Iy, another is Ix minus Iy, and so this is a slightly different way of writing the same thing. Okay, then we define a rotating frame, a very useful concept in NMR. Indeed, what we see as a signal in our oscilloscope after demodulation is what really happens in the rotating frame. And the rotating frame can be described by a transformation operator, which is given by E I omega IZT. And so your wave function in the rotating frame is given by T psi. And you can write down the Schrodinger equation in the lab frame and in the rotating frame. And the effective Hamiltonian in the rotating frame is given by this. And this is something that I should point out to you, that the effective Hamiltonian in the rotating frame is simply not given by, is not equal to TH T inverse. It is an effective Hamiltonian. You see what you calculate as comes out as after you substitute psi from here. And what it is, that it is the offset term. That means if you have the Larmor frequency of omega I, and you go to a rotating frame of omega, is the difference in the two frequencies that comes in as the chemical shift term. And the main reason for going into the rotating frame is to take away the time dependence from the RF term. The scalar coupling term remains unperturbed. Now, when we have the pulse and we make an assumption that the amplitude of the pulse is very much greater than the chemical shift differences, not the chemical shift, the chemical shift differences from the frequency of the RF, and that is also the frequency of the rotating frame, because we have gone to the same frequency as the frequency of the RF, and larger than all the J couplings. Then this is the same statement that I made yesterday, that the power is larger than the spectral width. And in that case, we make an approximation that the effective Hamiltonian in the rotating frame in the presence of the RF is simply the value of the RF along the x-axis. In a pictorial way, this can be seen in the following way, that you have the gamma H1 here, and the remaining chemical offsets and J coupling are of this magnitude. And if this is very much larger than these offsets and J couplings which are in the Z direction, then effectively you have an effective Hamiltonian along x-axis of magnitude gamma H1. And we will use this for calculating our result of an experiment. Okay, we use a concept called density matrix to describe time evolution of the magnetization in time domain NMR experiments. And since two-dimensional NMR experiments and time domain NMR experiments, it is very useful to use a density matrix. And for those who are not convinced why one should really use density matrix, I have a very brief reason for using density matrix. The need for density matrix it's from the book by Abraham, and I must put before you the two famous books on magnetic resonance, one by Abraham and one by Charles Richter, and these are fundamental books on magnetic resonance. I did not give them as a reference to two-dimensional NMR spectroscopy because they're really more basic than that. And so if you want to really know magnetic resonance in detail, these are the books to be looked at. And what I'm presenting here is from Abraham's book right in the beginning. And what he says is that if you have a collection of identical spins and you put them in a magnetic field, then at equilibrium, what you will see, there is a net magnetization along the z-axis, that is the direction of the magnetic field, and no magnetization in the perpendicular direction. But if you try to calculate, for example, the magnetization, the expectation value of mz, then it is given by the wave function times the operator, the integral of Iz, which is given by a1 square minus a2 square. And if you calculate the expectation value of m plus or m minus, or you can calculate mx or my, they are the same thing, then it turns out that m plus is proportional to a1 star a2, and m minus is a1 a2 star, where alpha and beta are the eigenstates of the system and psi is the wave function, okay, where alpha refers to the plus half state and beta refers to the minus half state. Okay, this result is somewhat disturbing because it says immediately that m plus and m minus is not equal to 0 unless either a1 or a2 is equal to 0, which means that all the spins are completely polarized, but that's not true. What we have, we do not have a complete polarization. We do not have same state of all the spins at equilibrium. What we have at equilibrium actually is that the sum total of a1i star a2i, take the ith spin and its value of a1 and a2 and compute this number, and sum total of all the spins is 0. So statistically this number is 0, not exactly, and therefore we have not really applied statistics here. And when we apply statistics into this system, then we see that this is the average over all the particles is what is 0. And it is really the average over all a1 mod square gives us the population of the upper level, and the average of a2 mod square gives us the population of the lower level, although sometimes we naively refer to this as population differences. But it is only the ensemble average that is the population. Therefore, to define things properly, we then define a matrix and call it a density matrix. I don't want to go into the reason why it's called density matrix. It's something to do with classical mechanics, but it is basically a matrix, and we define a matrix element of this density matrix, a rho mn is equal to an star am. And please notice that the subscripts here mn are in opposite order to nm here. This is important. And what it turns out that we only need to know the product, the quantity an star am ensemble average for any system. We don't need to know a1 and a2 separately and exactly. And this is sufficient for us to calculate the expectation values. The expectation value of any particular operator R is then simply given by psi star R psi d tau average. And then I substitute psi star as sum over n a n star psi n star, where psi n are the eigenfunctions, and R am and psi m. And what I get here is this quantity a n star am times the matrix element of the operator R in the eigenstates phi n phi m. So this I can represent, this number I can represent as R n m, and this we have defined as rho m n. And then we multiply two matrices and the n drops out, and it is nothing but a trace of rho n, rho times R. So we come to the, and I think this is not necessary, and therefore what we have here is that any operator whose expectation value we want to know, we just have to find out the trace of the density matrix with the operator. Okay, and so what we need to know to find out the quantities that we measure is what is the density matrix at a given time. And so the density matrix is what we need to compute. It is rather straightforward to see from Schrödinger equation. By substituting, one can come to it, and you can try yourself and find that you will get to this equation, which gives us the equation of motion or time evolution of the density matrix in a given Hamiltonian H. For those who are not familiar with commutators, I have a brief statement here that this bracket is a notation which says it's a commutator, which means nothing but these two operators, these are two operations, and one has to be a bit careful which operation you write first and which you write second. The notation means h rho minus rho h, and it is defined as commutator. And if rho h is equal to, if h rho is equal to rho h, then the commutator is 0. Otherwise, it is not 0 and has some value. What that simply means is that when you perform one operation followed by the other, is the result the same whether you do it the reverse. For example, if I want to wear the shirt and a tie, I must do a certain order. I cannot reverse the order. The result will be completely different. While I can wear the shirt and the shoe in whatever order I like. So the operation of wearing a shirt and the operation of wearing a shoe commute, while the operation of wearing a shirt and that wearing a tie don't commute. Okay, so this is basically two operations. Whether one can interchange them or not is what is commutator. Okay, we have defined this rho, which is a global rho, but we really need a spin density matrix, and we can take the trace of all the states of the lattice states, and we define a reduced density matrix, spin density matrix, sigma, and that's what we are really going to use. We're not going to use rho very much. It's for the relaxation people who need the rho, and we are going to work with sigma. Okay, and so sigma is what we all need, and the equation of motion of sigma is also very simple. It's exactly the same. This is actually a Schrodinger equation. It looks, it has some similarity to the Heisenberg presentation, but it is actually a Schrodinger equation. Okay, and from partition function, please note a spelling mistake in my notes, and please correct that here. And from the partition function, one knows the equilibrium value of the spin density matrix is simply given by the exponential of the various differences in the energy states divided by kT, or the trace of all the states. Then we make several approximations at this point, which are valid in high resolution NMR of not very low temperature systems. For example, we make a high temperature approximation saying this quantity is small, and then we make a high field approximation saying that J couplings and chemical shift differences are not important, and it's basically H naught that determines the whole thing. And so the equilibrium density matrix is given by 1 minus beta Iz, where beta is the gamma H cross H naught upon kT. This 1 never contributes to trace. So if any quantity, suppose you want to take an expectation value of any operator, then you will multiply the sigma with that and take a trace, and this will always give you 0. Therefore, this 1 drops out. And very often, even in research papers, you will see people say sigma 0 is proportional to beta Iz. But please remember that there is also a 1 there. You can drop it, but you can get into trouble when you are discussing the order of magnitude of things. Okay, so basically we know what sigma is. Let us see how the time development of sigma takes place. Now, it's very easy to see, and I'm not going to prove it, and these are one of those statements easy to prove, and then you can spend half a day trying to prove it, but I assure you it will take you only 10 minutes. That if H is time independent, then one can show the solution of this equation is very simple, and that is that the sigma at time t is e to the power minus iht, sigma 0 e to the power iht. And this is actually what we are going to use all the time. And we will transform ourselves into that particular frame where H is time independent. If H is not time independent, then we have a lot of trouble, and there's a lot of magnetic resonance theories which have been written down how to handle that. We are not going to come into anywhere near to those. So we are going to do the simplest of simple things, that is that it is just a unitary transform, and the time evolution of the sigma is given by e to the power minus iht, sigma 0 e to the power iht. You can show that this solution satisfies the equation of motion. Okay, only thing is the H has to be appropriate, the equation of motion has to be appropriate one. For example, during a free evolution, we have the free Hamiltonian, H free, and this is straightforward. During a pulse, tau, we had the equation of motion in the rotating frame. The reason being very simple, because it is only in that frame that the Hamiltonian is independent of time. And therefore, we write the equation of motion like this, and a solution which is given by this. Okay, what is sigma r t is t sigma t inverse, and hr is equal to gamma h1 ix, and that's what I showed you before. Okay, and then the rotating frame Hamiltonian is gamma h1 ix, and I substitute that, and then define gamma h1 tau is equal to the flip angle of the pulse, and that's what we did yesterday. And I just write alpha for that, and it is still same. And at this point, I substitute what I have, sigma r0. Now, sigma r0, that is the at time t equal to 0, what is the value of the sigma in the rotating frame? As you see simply that if I substitute t equal to 0 here, my sigma r0 is equal to sigma 0. Okay, and which is beta iz. And beta is number, it's not an operator, I can take it out anywhere I like. And so I have this quantity which says that the operator iz is transformed by a pulse of angle alpha along x-axis. And this is the simplest statement, that if alpha is equal to 90 degree, then we get iz transformed to ix or iy, depending upon the pulse was along x-axis, so it goes to iy.